Start recording for Adam. Okay, so again, one final reminder, just so you all hear it, and so Adam can hear it now too. Test on Thursday on 4.1 through 4.4. Got it, everybody? Yes. All right, and again, tomorrow we'll do a little review for that. Okay, but for today, what we're going to be looking at is, we're going to look at the sine and cosine as functions of x. Okay, so we saw this earlier. We did an example of just to see when we were playing around with the unit circle to see how you can use it to model things, about how we can turn these trigonometric identities into functions and how they work out from there. Okay, we're going to basically be picking that up, doing that more so formally today, and kind of going through the ins and outs of how the sine and cosine work as functions of x. Okay. Before we get, just to make sure you all remember, what's the sine going to be equal to in terms of the unit circle only? The sine is not x, y. Okay. The sine, remember, is equal to y. And what's the cosine equal to?
X.
That one's equal to x. Okay. So this is in terms of unit circle. Okay. So if I'm evaluating the sine or the cosine from unit circle, I just simply look to see what the y-coordinate is and what the x-coordinate is. Okay. That's kind of helps us speed things up a bit when we're doing these things. Okay. Here's the thing that's going to be tricky about this. Okay. Moving forward, and this is a part that I've seen a lot of people in the past get confused about. Okay. We're going to treat the sine and cosines as functions of x. That means theta here will be the variable that's changing. Okay, it will be the one that we get to put, that basically we get to choose. It's going to be the independent variable. And so the output, the dependent variable, is going to be y or x in this case, depending on what the unit circle tells us. So when we're graphing these as functions, okay, the angle will be the x-axis, and the y-axis will be whatever y or x is from the unit circle. Okay, so it's kind of looking at two different graphs at the same time when you're getting used to this for the first time. Okay, it's something to keep track of.
So you don't get both coordinates on only one. Yeah.
You're only choosing the one, right?
Yeah.
Okay, so the angle, so basically, I'm doing a graph of the sine as a function. Okay, the x coordinate is going to be whatever the angle it makes, and the y coordinate is actually just going to be the y you get from the unit circle. Okay. Everyone got that so far? Okay, so let's take a look at the basic examples of this. Okay, so we're going to look at, we're going to say f of x is equal to the sine of x. We're going to start with the sine of x because basically it's the one that kind of, we go back to that whole notion of the library of functions, the different types of graphs that we see. The sine of x is the graph type for this kind of category of graphs that we're doing, okay? Because the cosine ends up just being the sine of x graph, just nudged over a little bit, okay? So sine of x, okay? If I were to go ahead, okay, I'm going to go ahead and throw up a quick unit circle here. 0. We're going to do it in radians. When you do graphs of things like sine of x, cosine of x, you're typically going to be in radians. You hardly ever graph these things as functions in terms of 360. Occasionally it happens, but for the most part it won't. Okay. So there's our quick unit circle. Coordinates here are going to be what? What's the xy coordinate? 0? 1, 0. At pi over 2? 0, 1. 0, 1. At pi? Negative 1, 0. Negative 1, 0. And at 3 pi over 2? 0, negative 1, 1. 0, negative 1. Good. Keep you guys honest. Okay. So, what this is, so on here, x for my sine of x is going to be the angle I plug in. So it's going to be angles from 0 to 2 pi in this case here, okay? And it keeps going forward and backward, but we'll stick with the 0 to 2 pi, okay? F of x is going to be what the sine of x gives me. So remember, if I say the sine of pi over 2, that'd be 1. Because, again, the sine represents y, and that's how you get it from the unit circle. So what I'm going to go ahead and do is, before I go ahead and graph what the sine of x looks like as a graph, I just want to go ahead and just make myself a little quick chart to help me out, just to say what each point is, so we kind of get an idea of what we're doing, okay? So x here is going to be equal to whatever angle theta I choose. And f of x, of course, is equal to whatever the sine of that theta is, okay? All right, so if I chose 0, what's the sine of 0 going to be?
0.
Good. If I chose pi over 2, go ahead and grab that for me, thank you. It's going to be what? Say that again.
1,
1. Okay. If I choose, yeah, sorry, full house here. If you like, you could use, that would probably be best. Or I can get you the chair where the video is. That's one. Okay. At pi, what do we get?
That's it.
Sorry?
0 again.
0 again. Good. 3 pi over 2? Negative 1. And finally, if I come back around to 2 pi, what do I get?
0.
0 again. Okay? So, there's my, there's a little chart to help me see what the x, y coordinates are for when I graph this thing. So let's go ahead now, throw this on a graph, okay? And I do apologize, my drawings, this drawing is going to be particularly messy because I'm not very good at this drawing. Okay, but here would be where 1 is, there's negative 1 on my y-axis. On my x-axis here, I need the location 0, well that's easy, it's the origin. Pi over 2, we'll say pi over 2 is right here. This is not going to be the scale. Pi, make it right there. 3 pi over 2, and finally 2 pi, okay? And so we can just go through and mark our points off, okay? So we know we've got one at 0, pi over 2 went to 1, pi we came back to 0, 3 pi over 2 goes to negative 1, and 2 pi comes back to 0, okay? Now, when I connect these dots, is it going to be just with straight lines? No, it's going to curve, right? Because if I did other points in here, I would see it would make this nice curve. And so, you know, if I fill in some extra ones here, we'll go ahead and add, I'll add pi over 4 right there. Pi over 4 is equal to root 2 over 2 for the sine, which is approximately 0.7, 0.707, something like that. So 0.7 would be about right there. And so that can kind of give you an idea that we're going to curve up there like so, which means we should curve down here, curve down there, curve back up. Now, does it stop at 2 pi? No. Of course not. What would it do? Keep going. It would just do the same thing. So we would do it at 5 pi over 2. We'd be at the same location as pi over 2. So if we mark that. Okay. Come back to 1. Okay. And then at 3 pi, we come back down again and run out of space there. So it does that over here. What's it going to do over here on this side? It's going to keep doing the same thing again. So at negative pi, comes down to -1, then shoots back up again and does that. So, what does it make? What would we call that? A wave. This is in fact known as the sine wave. And you probably have seen this before, or have used this before. In fact, we're using it right now. What am I doing when I'm right now? Like, I'm talking, right?
Sound waves.
I'm making sound. Ah! So we have what? A
Sound wave.
sound wave. This is actually how sound works. Okay, when you speak or when you start talking, or when you play music or do anything, the vibrations through the air travel in a wave, and it's actually a sine wave. It's how it's modeled. And so that wave goes back and forth, back and forth, back and forth. And in fact, the various things you do to sound are actually manipulations from a mathematical standpoint of this sine wave. Okay, so I like to use kind of sound because everyone knows how that works to give you to do examples of the different parts of the sine wave. okay? Because it makes a nice correlation here.
So the transformations.
So the transformations all correspond to actual physical things, okay? And it's not just with sound. You could do this with light. You could do this with actually ocean waves, etc. Anything that kind of travels with a wave like this, okay, has that happen to it. But sound is something you all are very familiar with. And if anybody plays music, you're really familiar with this. So, gives you an idea. Okay, so, if we're analyzing the sine wave, it's got some various pieces and parts, okay, that we want to go ahead and look at, okay? The first one is something, is what's called period, and it's the distance it takes for the wave to repeat, okay? So this wave right here, its period is 2 pi, okay? You might be familiar with period as being wavelength. That's the same thing. So, you know, the wavelength of the sound or the wavelength of light actually is mathematically the period of the wave. It's how long it takes for the thing to repeat, okay? The other big thing we have here is the distance from the top of a wave to basically the x-axis, or the bottom of the wave to the x-axis in this case. I'm going to modify, it's not just the x-axis, it's something slightly different we're going to talk about in a little bit, but basically it's that distance right there, okay? Anybody know what this is called?
Amplitude.
Amplitude, good.
Yep.
Okay, this is amplitude, okay? And in fact, so what does amplitude correspond to in a sine wave? Loudness, which is called
Volume.
volume. Basically, volume is the same thing as amplitude. So the volume, when you turn up the volume on your stereo, you're actually increasing the amplitude of the sine wave coming out of the stereo.
So you're
Okay.
adding it on.
You're amplifying it, right? Hence why it's on a guitar it's called an amplifier. You hook up your electric guitar to an amp, it's coming from this right here. Okay, you're physically changing the amplitude, okay, of the wave. All right. So those are the two main pieces we're going to look at. There's a few other pieces as well. One is just like any other graph, just like any graph you'll see, this thing could have a vertical shift. We can move it up or down the x-axis. And when we do that, okay, if we moved it up the x-axis or down the x-axis, the amplitude goes with the line. It doesn't stay with the x-axis, it goes with whatever line you do, okay? So the amplitude is related directly to the vertical shift, okay?
Would the amplitude,
Let's say related to it, because it's not the same thing as the vertical shift.
so it would remain as loud.
Yes,
Oh,
okay? And a physical example of vertical shift when dealing with with an actual sound wave, like something from stereo. Your stereo's equalizer. If you have a fancy stereo with an equalizer that you can like pull the things up and down on, that's actually changing the vertical shift of the wave. So in that case, it can make it louder because I'm taking the entire wave and moving it up. But that's the kind of one of the things the equalizer can do is change the vertical shift. Yes. Yes, you may use the restroom. Okay. The other big thing that we have with this, with a wave like this, is it doesn't necessarily have to start here at 0, 0. I mean, I can move things left or right as much as I want to, right? Well, what do we call that when we're doing it with a normal graph? It's horizontal shift, right? Well, here we have a fancy name for it. Okay. Motion left or right. So if I move the entire thing left or right, okay, we call that phase shift. Okay, and this is basically the same thing as a horizontal shift. Okay, for this particular graph here. But the phase is just saying where I'm going to start the wave or end the wave. Okay. As far as sound is concerned, again, the equalizer in the sound system can change the phase shift. Typically that would be used more if I'm in a production studio with a lot of instruments playing at the same time. If I want to kind of sync things up so they at least sound more in harmony, you're monkeying around then with the phase shift, okay, the sound waves. In fact, another example of phase shift, auto-tune. When someone's singing with an auto-tune, part of that auto-tune is adjusting the phase shift because things like notes on a scale, things like pitch, they're controlled by phase shift and period. And so manipulating those things can make you sound either really good or really terrible, depending on how things work. Okay? But these are basically the pieces of the sine wave. Any questions so far? Okay. Let's look at how each of these graphical pieces fit into the equation for a sine wave. Yeah?
If we were to flip this, would that make something else? No.
Flip it as in like move it upside down?
Yeah, or change the coefficient to negative.
What that does indeed, all it does would actually, doing that would actually just change where the thing starts. So if I flip this thing upside down, it's still the same wave, it just starts down, it goes down first and then goes up.
Awesome.
But notice, I get the same effect
Yeah.
if I nudged it left or right. And that's kind of the beauty of waves, or at least a wave like this, is that they just repeat over and over and over again. Do this stuff. Okay. And so those adjustments there. All right. But if everyone understands these pieces, let's go through and talk about what they are from a physical standpoint. So I can think of a sine wave or a sine graph as being written as f of x equals k plus or minus a sine of bx minus h. Okay? Now, some of those letters up there should be familiar from the standard transformations we did with earlier graphs, right? For example, what do you think the k is going to represent up here? Up or down? It'll be vertical shift. Good. Okay? What do you think h is going to represent?
The vertical, the phase shift.
The phase shift in this case. Or it's going to be, you would use it to find the phase shift. Okay? And a up here, anyone want to take a guess what a is going to be?
Amplitude.
Amplitude, A for amplitude, good, okay? But notice how we got things a little bit different, like we've got this B in here now, okay? What's the only thing we haven't said yet associated something with? Period. B is going to control the period, okay? And so if I come through here, I can actually label what each of these pieces are on the equation up here, okay? So typically we start with amplitude and period first, because those are directly part of the actual function. Well, I guess it's all part of the actual function. Amplitude first. Okay. A for amplitude. So amplitude is going to be controlled by A. More specifically, it's the absolute value of A. Okay? Of whatever A is. Okay? So someone asked me what happens if it's negative. If I put a -3 in there, the amplitude is just 3. Because, again, all it's measuring is the distance between the top or bottom of the wave to the kind of the center line of the wave, okay? To where the vertical shift happened, okay? So amplitude would be A. Actually, I should also say plus or minus K out front, because K could be net. Well, no, I'm not going to do that. We'll get rid of that, okay? Because we can always define K as being negative. So amplitude, absolute value of A, okay? Period is the next one. Now we know period is controlled by B. Okay, we kind of used process of elimination to say, okay, B is the only thing up there I'm not familiar with. B is probably going to be period. It's not just going to be straight up number B though. Okay, actually, what it's going to be is the period is going to be determined by the whatever change I make to 2 pi to get it to repeat. If you remember the other day I said, when we were talking about the unit circle, I'm saying I can, the unit circle values kind of go through even if I change how quickly I make the thing repeat itself. Well, I can make a change to that by dividing the period 2 pi by b. So let's say if I divided it by 2, I'm halving the length it takes for it to repeat, right? So if I divide this by 2, that means it needs to get all of its business done in a distance of pi instead of a distance of 2 pi. Okay? If I divide it by 3, it has to be shrunk down from 2 pi to 2/3 pi. If I divide it by 4, it has to get all its business done in a space of pi over 2. Okay? So dividing by b, okay, changes how quickly it takes for the wave to repeat. So period is written as 2 pi divided by the absolute value of b, because again, it doesn't matter if it's positive or negative. If it's negative, everything works the same way. It's just, shrinking it, still shrinking it down, basically. Okay. That also means that when b is a whole number up here, it shrinks down the period. If b is a fraction, okay, it actually lengthens the period. So if I made b up here like a half, I'm doubling the amount of time it takes for the wave to repeat. Okay. So I'm basically making the wave repeat, the big, makes it even longer. Going back to sound waves, if I change the period of a sound wave, what am I changing? Someone had said it earlier.
Volume?
Not volume, that's amplitude. For example, if someone has a high squeaky voice, frequency, okay, frequency is close to it. What do we call that in sound? Pitch. Pitch is what you're changing. So actually, when you make changes to the period of a sound wave, you're actually changing the pitch of the wave. Okay, so shrinking the making the pitch smaller makes it sound higher. Making it longer makes it big. So that kind of low, deep bass, those are really long sine waves. Okay, which means b has become a fraction. Okay, a quick high pitch means b is a large number, and we're shrinking the wave down very quickly. But that's how period is determined. Okay. Any questions about that?
So the octaves are actually the eighths. The octaves are actually the waves that actually land on top of each other and have the same notes.
I didn't know that. There you go. Okay. The more you know. Okay. Period. All right. Next one up. K. Vertical shift. That one's easy. And is it going to be anything special? Nah, it's just whatever K is. Okay. So if K is 5, I move the wave up 5. If K is -7, I move it down -7. Okay. Yeah.
One period. So was it larger b equals lower pitch?
No. Larger B equals shorter wave.
Shorter. Okay.
Yes. Because I'm thinking of it this way. As B increases, I'm increasing the number of times it takes to repeat,
Yes.
or how quickly it will repeat, basically. So the larger B is, the faster the thing repeats. Okay, which increases the pitch. Okay, and the smaller B is, the slower it takes for it to repeat. Okay, so when B is like a fraction, and again, sign doesn't matter. So if I put a really big negative number, it just makes it repeat really quickly as well. Okay. All right. Yeah, vertical shift works normally. All right. Last one is this thing called the phase shift, which is the same thing as a horizontal shift. Basically, they work the same way. Phase shift, it's tending to just be like, oh, it's whatever h is. It's not quite though. Okay. Why would it not quite just be h? There's that b in the way. Okay. And so the phase shift is that basically is you would set bx minus h equal to 0 and solve. Okay? Whatever x then comes out to be, that's your phase shift. Okay? And so it's telling you how, basically what it's telling you is the location I'm now starting the wave at. Okay, it's what it tells you. So this basically tells you the location I start the wave at. Space. Okay, so if I did an example of all these things in the same problem, if I wrote up a sine, we could go through and identify all these parts, which would then help me when it comes out to actually graphing the wave. Okay, so let's look at an example. We'll say, let's start off with an example of these. We'll do f of x equals I like 4. 4 minus 2 sine of, sine of 3 pi, or 3x, excuse me, minus pi, okay? So, let's take a look at how this thing would look at right here, okay? First, my amplitude would be what? Just 2, okay? Now, that minus sign will affect the graph. It just means that when I start, I go down instead of up, okay, when I start off, all right? So my amplitude, which I'll abbreviate as amp, is 2. What's my period going to be? 2 pi over 3. Okay, which means that this graph is going to repeat in a distance of 2/3 pi instead of a distance of 2 pi. Okay? We good back there? Yeah. Okay. Vertical shift, nice and easy. What's it going to be? 4. If you want to be fancy, you could say it's y equals 4. I don't really mind too much if you left off the y equals 4, but you know, technically speaking, that's what it should be. Okay, and the phase shift. The phase shift, remember, is going to tell you my new starting point. Okay. How would I figure that out? I set 3x minus pi equal to 0 and get pi over 3. Okay, so that's telling me now where my thing starts. Okay, I'm going to start the graph at pi over 3 now. Okay, so if I come through, I'm going to let you guys copy all that down. Then we're going to actually graph this thing. Okay, based off this info here. Okay, everyone got this down?
Yes, sir.
Okay, so here's that graph. So graph of f of x equals 4 minus 2 sine of 3x minus pi. Okay, so going through here. Okay, I'm going to go ahead. First thing I'm going to do is mark my vertical shift. Okay, so it's at 4, so it'd be 1, 2, 3, 4. I'm going to go ahead and just put a dotted line at 4. This will just help me when graphing. And what this little dotted line is going to tell me is that that's kind of a new horizontal axis for my wave. So when my wave, the line is going to now do its waviness around. I don't know what the proper term for waviness is. But the thing it's going to wave around is going to be the line y equals 4 instead of the x-axis. Okay? So that's kind of the purpose of the vertical shift. The next 2 lines I'm going to do here, and this is a trick I learned kind of how to work these things out, is our amplitude is minus 2, or our amplitude is 2, excuse me. So that means the lowest this thing can ever go from the line 4 is 2 down. So the lowest it could be is somewhere along y equals 2. The highest it could be would be 2 up. So y equals 6. So I'll go ahead and add dashed lines along there. And this, again, these lines, besides these 2 dashed lines, are just to help me when I'm graphing, because my graph is going to stick with inside that zone there. Okay? So this also did me a great thing. What have I just done here?
It's your range.
It's my range. I've also gone through here and defined the whole range of this thing. And I've gone ahead and defined it. So my range is going to be y between 2 and 6. Okay? That was sort of a nice thing to have done there as well. So hey, kind of get range as a freebie there. Okay? Good. Now, the next thing we've got is a starting point. The starting point was pi over 3. So here's where 0 is. We'll call this pi over 3 right here. Okay? So that means I'm going to start at that location right here. So this is pi over, this point here is pi over 3, 4. This is the starting location for my graph, okay? Then, the next thing I learned was that it takes a distance of how long to repeat?
2 pi over.
2 pi over 3, that's what we figured out before. So, that means if I add 2 pi over 3 to this, I'll get the location where it's gone through one full circle. So what's pi over 3 plus 2 pi over 3?
1.
1, it's pi, right? So, pi over 3, we'll say pi over 3,
Yes, to those.
guess we'll just put it over here as pi. This scale is not going to be, I'm going to have to go through and kind of do a better job. I'll have to do a better job in the future graphing these things with a scale, okay? Because obviously, my doing it by sight is not going to be very good. Okay, so that means that between pi over 3 and pi, we're going to have one full cycle of this graph, okay? Now, to kind of fill in the rest of it here, okay? Since I want to have the points in between so I know kind of the major checkpoints, if you will, like where the thing has its first minimum, where the thing has its first maximum, where it comes back to that center line again, those are actually not as bad as it seems. The center, where it's going to return to the center line for the sine graph is going to be the point that's halfway between pi over 3 and pi. So what's halfway between pi over 3 and pi? Is it 2 pi over 3? Yes, yes it would be. Huh, so that's how it came out to be. So here at 2 pi over 3, we should come right back to the center line here. Okay? Now, then halfway between these and halfway between these is where I'm going to have a maximum or a minimum. So what point's halfway between pi over 3 and 2 pi over 3? Be a pi over 6 point, right? So I can think this is 2 pi over, this is 2 pi over 6, this is 4 pi over 6, so it'd be 3 pi over 6, which is pi over 2. Okay? So at pi over 2, 2, I have a minimum. Now, how do I know I'm going down instead of going up first?
Because of the negative.
It's again that minus sign right in front. It's telling me I'm going to go down first. So, even though when you're calculating amplitude, you're doing an absolute value, and you leave, and you don't really care too much, amplitude is just going to be whatever the number is, the sign still matters. It tells me do I go down first or do I go up first. Okay? Same way as things usually. Okay, what's the point halfway between 2 pi over 3 and pi? 4 pi over, this is 4 pi over 6, 6 pi over 6, so this one right here is going to be 5 pi over 6. And 5 pi over 6 is going to come up to right there. So 5 pi over 6, 6. Okay? And so I can connect the dots. And so this thing has a sine wave that looks like that, and it's going to repeat. So it's going to come back like that. And if I was better at drawing, I would mark those locations, but we get the general gist. So there is one full cycle, okay, of this graph, and how you would use all those pieces to help you graph, okay? Any questions on how that works? Okay, so kind of looked at the first step when I graphed this. Besides just knowing what the sine graph should look like, my first step was going through and finding all the pieces, saying, what's the amplitude? What's the period? What's my vertical shift? What's my phase shift? So once I have all those down, then it's just a matter of putting out kind of the common points where this thing has its terms. Okay, I know for a sine graph, it returns back to the center point halfway through my period. I know it has maximums and minimums at the quarter and three-quarter part of my period. Okay, and so using all that, I can get a great picture of what's happening to the thing by hand. Okay, any questions about how a sine wave works? Okay. Let's see, we've got a few minutes left, so the other one we want to look at today is the graph of the cosine. And guess what? All the pieces of the graph of the cosine are the same. Okay? So basically, I could come through instead of writing cosine x, I could write this as k plus or minus a cosine of bx minus h. The cosine graph is going to have all the same pieces. So it's amplitude still the absolute value of A, its period is still 2 pi over B, its vertical shift is still whatever K is, and its phase shift is still Bx minus H equals 0, okay? Now, all those parts are the same. Does anybody know what the difference is going to be between the cosine and the sine, as far as the graph is concerned?
X and Y.
Okay, so one's using x's instead of y's. So if I go all the way back to my unit circle, from the very beginning here, oops, okay, right here, when I start with the cosine, am I starting at 0? Starting at 1, then I hit 0, then I hit -1, then I hit 0 again, before coming back to 1. So it's going to do the same wavy picture, but it's going to not be mirrored, it's going to start at a different spot, okay? Instead of starting at the baseline for the thing, it actually starts at a maximum or a minimum. That's where it's going to start, okay, depending on how the thing's written. So, coming all the way back through, oops, if I looked at the basic f of x equals cosine of x graph, okay, there's 1, there's -1 for y, here's 0, pi over 2, pi, 3 pi over 2, 2 pi, okay? All I'm going to be doing is it will have the same wavy shape as the sine graph, except it starts up here at 0, 1, instead of at 0, 0, okay? At pi over 2, it's at 0. At pi, we're at -1. 3 pi over 2, we come back to 0. And at 2 pi, we come back up to 1. Okay? So if I were to draw that out, it'd look like that there. And it's a wave still, so keep going like that, okay? In fact, this thing, okay, is still as far as it's concerned as graph types, it's still a sine wave, okay? It still makes that sine wave picture. The only difference is I've started here instead of starting here, okay? So I can actually come up here and say that the cosine of x graph is equal to the sine of, basically, we've moved everything over to the right pi over 2, right? Sorry, to the left pi over 2. So it'd be like adding pi over 2 to the graph. So I could say it's the sine of x plus pi over 2. Okay? Gives me that picture. Okay? And notice that's exactly what it would be. Okay? There's actually an identity based off of this that we'll see kind of later on, telling you the kind of the relationships between the cosine and the sine as far as the graphing is concerned. Okay? But other than that, it's just that slight phase shift over. Otherwise, the graphs are the same. Okay? Any questions about how cosine works then? All right? So, if I'm going through, if I gave you a cosine graph with actually filled in with all the pieces, you do the same exact analysis as you do with the sine. Just remember that when I start it, I'm going to start it either at a maximum or a minimum, and not at that center line. Okay? So, from maximum to maximum would be one full cycle, or from minimum to minimum, if it started going down first, would be one full cycle. And the halfway point would be the maximum or minimum again. And the quarter and 3/4 points would be where it crosses the baseline. Okay? Otherwise, same sort of graph there. Okay? All right. Any questions about this so far here? Got it down? All right, excellent. We've got about 3 minutes to spare here. Does anybody have any questions on last night's work? Okay. It was just more of the same of what we've been doing over the last couple of days, just getting used to how how to use a unit circle to find values of things. It should have been really, again, since it was the same stuff we've been doing the last couple of days, it should have been just more review.
Yeah.
Okay. No specific questions?
One question about this.
Okay.
On this graph, you can only find the x value of the coordinate, right? Like,
Well,
you
what
said
we're
something about angles. Okay.
well, what we're mapping out here,
Yeah.
basically these, the output here,
Yeah.
those are the x coordinates from unit circle. The angle is what the first number is. That's why it goes from 0 to 2 pi over 2 pi. So,
Okay. So, but that's you can't
So-
find the y in any way.
well, if I know
Well,
that pi over 2 is here, I can go back to unit circle and say, okay, if I'm doing the sine, it should be y should be 1 there.
That's true.
Okay.
Perfect.
You could always, but that's not what the cosine is graphing. Cosine's dealing with what the cosine deals with, and the cosine of the unit circle deals with x. Okay.
That makes sense.
Nothing else there. Okay.
Sweet.
No questions about the stuff from last night? All right, I'm gonna go ahead and let you guys go to your next class. Okay. So trying to do something new in 2 minutes. Okay. Y'all have a good day.